Good morning, class. This is Cement and Ags. This is Learning Plan 2 under lecture. This is going to be part 2, so we're going to go through the second half of this PowerPoint here. Okay, so there we go. Let's talk about a sieve analysis. So a sieve analysis, sometimes they call it a gradation. Okay. Basically what this does is we call it a gradation curve. This is the most useful engineering property for aggregates and soil mechanics. We can define our aggregates very well, and we can base a lot of our engineering properties off of this. So the first step, what you want to do is basically what we're going to grab a sample based on ASTM D75, and then we're going to reduce it again to a certain size based on the aggregate. We're going to dry the sample. We're going to weigh and record and dry the sample weight, wash the sample, dry again, sieve the sample through the sieve nest, weigh the amount of material retained in each sieve, calculate the weight retained in the pan, calculate percent retained on each sieve, and then calculate cumulative percent retained on each sieve, and then calculate percent passing. Okay, so that's a really quick summary of the steps. We're actually going to perform this lab. This will make more sense when we actually do it, and then I'm going to go through the calculations here. So let me go to slideshow from current slide. Okay. All right, so let's do an example so you can complete your homework. All right, so if we look here, and I'm going to switch to my document cam. An unwashed dry silty sand sample weighs 1,500 grams. After washing, drying, and sieving, the following weights are measured on each sieve. Okay, so basically each of these sieves, we dump it out and we weigh it on a scale. Okay, now you notice the first, okay, calculate the pan weight and percent passing for each sieve. So you notice there's a blank spot here on the pan. Okay, reason why that is remember, we dry, when we get the sample from the field, we dry the sample. Okay, then we weigh the sample. All right, so that is what that sample is. Okay, so when we wash the sample, we're washing it over a number 200 sieve. So if we remember, fines pass through a number 200 sieve, the silt and clay. So we're washing that away. So some of our 1,500 grams is actually being washed down the sink. So when we say pan, it's actually a pan. It's a closed sieve that the remaining of the material actually catches. Okay, or the pan that catches. Okay, so how do we calculate what was actually in the pan? So, for example, if we put that pan underneath our wash water and we dried it out, all that material would be in a pan, but we don't. Okay, we wash it down the sink. So what we do is we add all this up. Okay, and we subtract from there. That is the amount of fines, weight of fines that pass the number 200 sieve. Either it's that we wash down the sink. Okay, so with that, I am going to go and we'll talk about calculations. So let me go to the document cam. All right, so, and then we're going to, all right, so if I look here, here's the same problem. Let's see, let me zoom in a little bit. Okay. Okay. All right, so if I look here, so to solve the pan weight, which is, so here's 9A9, so I kind of using Excel, is the sum of, let's see, let me start over. We're going to take 1,500 grams, that's our unwashed weight, minus the sum of A1, right? A1 through A8. Okay? So if I do that, that equals 1,500 grams minus, okay, so we got 11.0 plus 180.0 plus 200.0 plus 210.0 plus 300.0 plus 310.0 plus 180.0. Okay, so first I got to add all these up and then subtract it from 1500. Okay, so when I do that, so 11 plus 180 plus 200 plus 210 plus 300 plus 310 plus 180 equals 1391. So now I'm left with 1,500 grams minus 1,391 grams, and that equals 109 grams. I'm just going to double check to make sure I did not make an error. Okay, so I'm going to add these up quick. 11 plus 180 plus 200 plus 210 plus 300 plus 310 plus 180, 1391. Okay, so now I know A9. So the weight of the fines which we wash down the sink is 109.0. So you notice 1 decimal place. So I got to put my 0.0 here. 1 decimal place. So if I come up here, 1 decimal place. Okay, so that's for this row and for this row, and we'll talk about the percent passing. Okay, all right, so now how do I get percent retained? Okay, so again, this equals weight retained in pan. Okay, so now I'm going to scooch this up a little bit so you can see it. So B1, so I'm going to, okay, so I'll just put that there. All right, so does that make sense? So this is first thing you need to calculate. Okay, now we need to go percent retained. Okay, so B1 equals, so I'm going to take A1, number A1 is 0.0, divided by my unwashed weight, which is 1,500. So that equals 0.0 divided by 1,500. And then we multiply it by 100. Sorry, I forgot about that. We multiply it by 100 times 100 to get it in a percentage. 1 decimal place. Again, 1 decimal place for this column when you're weighing it on a scale, 1 decimal place when you're weighing it on a column on this scale, or when you're calculating this. Okay? All right. So I get, so obviously 0 divided by any number equals 0.0%. Okay? So this number is 0.0%. So now to calculate B2, I'll just do another one here. B2 equals the A2, the number in A2 divided by 1,500 times 100, which equals, so the weight retained divided by 11.0 divided by 1,500 grams times 100 equals, okay. All right, so 11 divided by 1,500 times 100, and I get 0.7%. So remember, if I want to round to the 10th place, what do? I look at the 3rd place. So I'm reading, if you look at my calculator here, I'm reading 0.733, oops, times Hold on. Let me do that again. I probably didn't multiply it by 100. 11 divided by 1500 equals, yes I did take it times 100, times 100 is 0.733. So that is taking it. So 1 decimal place, so this is a 3, 5 or higher, this would turn into 8, so that is 0.7%. So to calculate percent retained equals weight retained divided by dry unwashed weight times 100. Okay? Okay, so basically 0.7% of that sample was retained on the number 8 sieve. So the number retained, right, is what's on top of it. All right? Okay, so now let's do the rest of them. I'll do it out loud here. So to calculate B3, I take weight retained divided by 1500. So I take 180 divided by 1500 times 100, and I get 12%. So that is 12.0%. I need 1 decimal place. Next one, 200, all right, divided by 1500 times 100 equals 13.3%. Okay. Next one, the number 30 sieve, 210 divided by 1500 times 100. Oops. 210 divided by 1500 times 100. That's 14%. So I don't have any decimal places, but I always want to have 1 decimal place. 14.0%. Okay. So I'll just show you how. So this guy right here, 300 divided by 1500 times 100. Order of operations, so that's 20%. 20.0%, right? It's an even number. So I'll take this one, 310 divided by 1500 times 100. So 20 point, so I want 1 decimal place here. So this is a 6, so that's 5 or higher, so that's going to turn to a 7. 20.7%. Okay. And then the last one, or 2 more, 180 divided by 1500 times 100, as again, is 12%. And then percent retained in the pan, 109 divided by 1500. Okay. Times 100. All right, so if you look here, 7.2, I'm going to round this up to a 3 because this is 5 or higher. Okay, so 7.3%. Okay, all right, so that's how I do column B, percent retained. Okay, so now let's go to cumulative percent retained. All right, okay, so again, this is 1 decimal place. So you notice 1 decimal place, 1 decimal place, 1 place. This is cumulative percent retained. Okay, so basically what a cumulative is, so remember I have a nest of sieves, right? So if I dump that sample in the nest of sieves, okay, I'm going to have weight retained on each one. Now, what would happen if I just left the pan on the bottom, something to catch it, and I removed all the sieves in between, right, and I dumped it, 100% of it would fall in the pan, right? So basically what it is, so for example, if I want to know cumulative percent retained on a number 10 sieve, is I'm going to pretend that I dumped the sample in, but I removed the number 4 and the number 8 sieve. So those aren't going to be retained anymore on those sieves, so they're going to fall right onto the number 10 sieve. So that's what cumulative means. So as I go down, this cumulative number is going to get bigger until pan where I should have 100% of our sample. Okay? So to do that, okay, so I have 100% passing, 0% retained on the number 4 sieve. So that means there's nothing also retained on cumulative. So that's 0.0, okay? So now to calculate C2, okay, this is cumulative percent retained, okay, is I'm going to take C1 plus, so I'm going to draw a little arrow here, C1 plus B2. So that equals 0.0 plus B2, so here's number 2, B2, plus 0.7 equals 0.7%, okay? So 0.7%, all right? So basically I took this one, added to there, that equals that number, okay? Now to calculate C3, okay, so this is C2. So C3 is I'm going to take C2 plus the next sieve. So again, see, I'm taking this and going this way, plus B3, and that will equal, so C2, so the previous, so I have cumulative, all right, so I have 0.7%, so I need to add that to what's retained on the number 10, so then so this plus this basically will plus 12.0%, and that would equal 12.7%, okay? And then I add that 12.7%. So that's how you do that. So literally you add this, that equals that. Add this to this equals that. So it's just like I'm taking out the sieves, cumulative. So, all right, so you can watch me use my calculator as I go through this. So to calculate this, so that's cumulative percent retained. 12.7 plus 13.3, so this is 26.0%. I'm going to take that one and add the amount of material retained on the next sieve, plus 14, so that's 40.0%. This will be, I'm just going to do this so it stays in my calculator. This will be 60%, 60.0%, right? 40 plus 20 equals 60. And then I'm going to add 20.7. This is 80.7% plus 12, 92.7% plus 7.3 equals 100.0%. Now, depending on your rounding, because you may round these numbers because I need it to the tenth, so you're either rounding up or rounding down, this number will be between 99.9% and 100.1% due to rounding. Once in a while, if you're always rounding up, we may go above maybe 100.2%, but that's rare, okay? So if this number does, this cumulative percent retained in the pan, does that make sense? That should be 100% of the material. It's basically, I took all this sample and I dumped it out and it should be sitting in the pan. This is a math check that I did my math correctly. So if this number is not between 99.9% and 100.1%, you did something wrong. So I want you to actually write the number you get right there. That is a check. And if that happens, what you're going to do is you're going to erase all this, you're going to erase all this, erase everything, and start over because you made an error somewhere. Okay? So that's how you do cumulative percent passing. Or retain, I'm sorry, retain. Okay? So that's the trigger. All right, so now let's do column D, which is percent passing. So I'll write it down here. percent passing equals 100 minus cumulative percent retained. Okay, so if I want to calculate D1, so get up here, equals 100 minus minus 100 point, or 0.0, and that equals 100%. So I'm going to talk about the decimal place at the end here. Okay, so again, this guy is 100 minus 0.7. Okay, so percent passing again is 100 minus cumulative percent retained. Okay, so 100 minus 0.7, should be able to do this in my head, minus 0.7 equals 99.3. Well, I'll start talking about, you notice what I'm doing here? There's no decimal places. These are whole numbers, except number 200 civ. There's a special thing with that one. Okay, 100 minus 12.7, 87.3, that's less than 5, so this is 87%. Okay, 100 minus 26, that's 74%. This will be 60%. Right, 100 minus 40 is 60. 160, 100 is 40%. Okay, the percent passing should get smaller and smaller as I go down. Okay, the cumulative should increase as I go up. And just check. All right, so 100 minus 80.7, so 19.3, but we're going to 19%. All right, so then the last one here is 100 minus 92.7, 7.3%. Okay, 7.3% of my sample passes the number 200 civ. Okay, so 7.3% of that entire sample has fines in it. Okay, so there's silt and clay in 7.3% of the sample. All right, so so from D1 through D7, D1 through D7 equals whole number. Okay, and then column D8, or the number 200 civ, greater than 10.0% whole number, less than 10.0% 1 decimal place. Okay, this only applies to the number 200 civ. Otherwise, the rest of these are whole numbers. Okay, so we just calculated, so we just did this first example. Calculate the pan weight and percent passing for each civ. That's what we just did. This is what your data will look like. Okay, next thing, we're going to plot the percent passing versus civ size on a semi-log graph. Okay, so I'm going to just take a short break, and I'll be right back, and we'll continue on. All right, welcome back. Okay, so now we're on this step right here. Plot the percent passing versus civ size millimeters on semi-log graph. Okay, so if we look here, this is a semi-log graph paper. I have this attached in Blackboard. Okay, so you can print this out. So let's start with the x-axis. So we can see the, all right, so if you look here, I'll use my pencil as a pointer. If you look here, semi-log It's log base 10, okay? I don't know if you remember this from mathematics, but if you look here, you see 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 9, 8, 7, 6, 5, 3, 2, and you see divisions in between here. So there, it's in, you can see it's kind of grouped in tens here, okay? So basically that's the x scale is in log, or the x-axis. The x-axis, which is the horizontal, is in log, okay? The y-axis, it's not going to be in log. We're just going to round it. It's just going to be no scaling, no log scale at all. So the y-axis is not log scale. So that's why they call it a semi-log, okay? So the first thing what you need to do is set this up, okay? This is why you need straight edges, all right? So what you're going to do is you're going to start, I'm going to make a so what you want to do is you want to start your y-axis on a whole number, 10, this one, this one, this one, this one, okay, on the ones, okay? So I'm going to start mine here. It should fit. So you may need to expand it. So I'm going to start it here. I'm going to keep extending it. All right. And then I'm going to make up my y-axis starting right here. Okay. All right. Okay, so here's my x-axis, here's my y-axis. So how do I set up my x scale? So the x-axis is the sieve size in millimeters. This is why I'm having you remember the sieve size in millimeters. So you got to convert the sieve sizes into millimeters, okay? So I got to look at the range of millimeters here. I go from 0.075 millimeters up to 4.75 millimeters, okay? So look at the decimal places there, all right? So if I start, okay, so if I make this 10 right here, that is going to represent 10 millimeters right on my 0, 0 point, okay? So that means this is 9, 8, 7, 6, 5, 4, 3, 2, okay, 1 millimeter. So if I put a little dash here, that's 1 millimeter, okay? So does that fit there? So 4.75 millimeters, so I go, so it's going smaller to the right. So if I go, I have 1 here, I have 2, 3, 4. See this little line right there in the middle? That's 4.5, so halfway in between there is 4.75 millimeters, okay? So now if I keep going backwards, this is 1, so I'm going to put 1.0, so you know it's a whole number. Now, what's the first decimal place less than 1? So isn't this 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1? So this next set of 10 right here is 0.1. Okay? And then if I go again, this is 0. Okay? So this is 0.09, 0.09, 0.08. Okay? So basically I go to the next 10, right? 0.0, whoops. This is only one. 0.01. Okay? So what's happening to the decimal place? It's moving. What is it moving? It's moving one spot to the left. 1.1, 0.01. As I go to the right, the decimal place is just moving to the left. Okay? So 10, 1, 0.1, 0.01, right? Okay? So if I look, I can make sure, see my largest sieve, which the first sieve that passes 100%, this is my maximum size right here, and then this will actually be my nominal size, right? Because I don't have all of it passing, but I have most of it passing, Okay, so I can fit my 4.75, 4.75 fits in there, and then my smallest one is 0.075. So if this is 0.01, this is 0.02, 0.03, 0.04, 5, 6, 7. 0.075 is right there. Okay, so that's how I set up my x-axis. Now, so that is percent passing versus sieve size. Okay, so that's my x-axis. Now my y-axis, so this is 0, so this is going to be 10, 20, 30, 40, 50, 60, 70, 80. I suppose you can't see what I'm writing now, so let me zoom out. There we go. 80, 90, 100. Okay? So I'm having 0% passing, because that's as small as I can get, all the way up to 100% passing. So that's why this is my y-axis. Okay, that is not logged. Okay, so I want to do an axis label. So you can call this, use these as guidelines. Sieve size, all capital letters, nice and neat. And then you always want to put units, millimeters. Okay, and then this guy is percent passing. So my units is percent, right? Okay, so you got a x label, x-axis label, a y-axis label. Okay, so now we got this set up. So now what you're going to do is we're going to plot this. So I'm going to plot percent passing, column D. This is my y-axis, and then my mesh size. Grain size, mesh size, sieve size, they all mean the same thing. Okay? So mesh size, and this is my x-axis. Okay? All right. So first thing you're going to do, so number 4 sieve is 4.75. So here's 1, 4, 4.5, 4.75, and that's 100% passing. So I know, so this is where you use your straight edge so you don't wander your line. Okay, that's 5. So this is 4.5. So in a sieve analysis plot, you only need your first data point has only one that is 100% passing. Because in theory, any sieve bigger than the number 4, it'll also be 100% passing, won't it? So literally it'll be a straight line across. If any sieve size, or I'm sorry, it'll be a straight line going this way, because the sieve is getting bigger this way. Okay. All right, so I plotted that one. Number 8 sieve is 2.36. So here's 1, here's 10, here's 2. This is 2.5. So you can actually, it's even divided. So this is 2, 2.1, 2.2, 2.3, 2.4, 2.5. 1, 2, 3, right about there, somewhere in there, right? And then we have 99% passing. So again, this is tough. I know I need to be, here's my, I'm going to go to my 99, 2, 4, 6, 8, 10. So this is 2, 1, 2, 3. So and 99% is about halfway in the middle there. Okay. Next one is the number 10 sieve. That's 2.0 millimeters, and that's 87%. At least that one's right on here. So here's one number. It gets larger to the left. 2.0, 82, 84, 86, 88, so 87. I'm putting this a solid dot. 87%. All right. Next sieve is 1.18. That's my x-axis, and 74%. So 74%, 1.18. So here's, so that's pretty close to 1.2, right? So if this is 1, that's 1.5. So it's right about there. Okay, so again, I use my little straight edge here. And we have 80, let's see, 1.18 is 74%. Okay, 2.4, this is 1, 1.1, 1.2, 1. So right about there. Okay. All right, next one, 60%, and then we have the number 30 civ, which is 0.6, and we're at 60%. 0.6, so 0.1 to 1, so this is it right here. So here's 0.6, and then I go to 60%. Again, I'm making sure. There we go. All right. And then my next sieve is the number 50 sieve, which is 0.3, and then that is 40%. So 0.3, here's 0.1. Remember, it's getting smaller to the right. This is getting bigger this way. Don't mix those up. So here's 0.3, right? 0.1, 0.2, 0.3, and then we're at 40%. Okay. All right. Okay. Now, the next one is the number 100 sieve, which is 0.150, and we're at 19%. 0.150. So this is 0.2. So obviously this would be 0.1, 0.11, 0.12, 3, 4, 5. So 0.150. And then again, we were at 19%. So here's 20, here's 18, and it's just below that. Okay. All right. So then the last sieve is 7.3%. So obviously we can't. You got to get it close because the scale is so small. You got to get it close. Okay. So now that is the number 200 sieve, which is 0.075, and we're at 7.3%. 0.075. 0.01, 2, 3, 4, 5, 6, 7, because 0.7, here's 0.08, 0.07, 0.08, halfway in the middle, and 7.3%, that's 2, 4, 6, 8, so right about there. Okay? All right, so that's how we plot that. Now the next step is you want to use a circle template. And you want to use one size. Okay? I'm going to use the 17/32, and what you're going to do is you're going to draw a circle around each of these points. Okay? Using the same size. Center your dot in the middle of it. Okay, as you can see what I'm doing here. The reason why I'm having you do this by hand, we can do this by computer, but you need to understand how this is created, because you need to know, does this look reasonable? Is the computer putting out a reasonable answer to me? Okay, that's why we do this by hand. All right. Now, basically what I'm going to do now is use a flexible curve. This guy, see, because it flexes. And now what I'm going to do is going to connect all the points. Now it's very imperative that I do not draw my line through the circles. I connect. Okay? So the key to this is you just connect 3. So I know this first one is tough because it's almost a straight line, so I'm just going to do 2. So see what I'm doing here? I'm trying to bend it so I can connect this third point. And then it's a pretty sharp curve. And you want to get it, the dots, so you want to get it in the center. Remember, your curve cannot go above 100%. So what I'm going to do is I'm going to kind of cheat, because this first point is always the hardest. Okay. Okay, see what I'm doing? I'm not, all right? I'm not going through the entire circle. Then what I'm going to try to do, okay, I'm going to try to match these 3. So this first sharp curve is kind of difficult. So now, I'm just going to use the bottom here. See what so I'm going to match these 2, And then I'm going to bend this, so because sieve analysis curves don't have any sharp curves, okay? So I'm going to match this to and try to go to this guy. There we go. See? All right. So I go like this, and then I go like this. Okay. So it's kind of weird. It's tough. All right. So now what you want to do when you want to connect this point to this point, you're going to match your flexible curve to these previous 2 points. Okay. Because what that will do is it'll create a smooth transition. So I match the curve here, my previous line. Okay. And then I start bending this, and I get it to the center of this guy. So I'm going to have this step to the side here because it keeps hitting me. So I kind of put my hand down. All right. Okay. Now if I want to connect from here to here, I can just leave my hand on this thing. So I want to match the curve from the previous 2 and then bend to the next one. Okay, see what I'm doing? I'm just kind of keeping my hand down. See, now this is kind of, and then this is what he's for. Okay? So, this guy, I don't know if I like that guy. So, I'm thinking this guy. So, you see how this is an upside down curve? I don't really like that. This looks weird, right? So don't be afraid to erase. And so I'm going to connect this curve, and basically I'm going to see if I can go my back up to here. So I'm going to match. I'm matching these 3. The more you can match, see, and then this might be a better fit, maybe. It's tough. So, okay, all right. But you can kind of see this as, so that's how you plot a sieve analysis curve. Okay. So if you erase this line, so basically you just. So again, the easiest thing is to do is to match the previous 2 and go to the third. Match the previous 2, go to the next point. And then if it looks weird, you can erase and try to make it look like a transition. Because in nature, our aggregates will not do a sharp curve like that. Okay? So that's how we plot a sieve analysis. Okay? So I'm going to take a little break. We're going to go over a little bit more lecture. And then we'll... All right. Welcome back. So let's talk about coefficients. So, all right, the sieve analysis plot. So when you look at the curves, so if you look at the gap grades, so as you can see here, here's grain size, the grain sizes, and here's percent passing. If you look, this is called gap graded because all of a sudden the curve will drop down because it's missing sieve sizes until it gets to here, and then it goes back, and then it misses again. Okay, so it's kind of like the slide at Bay Beach. It goes woo woo. All right, so that's gap graded. So these identify when I plot it out, I can identify my curves. Okay, a well graded means there's all sizes from small to large. Okay, small to large. So as you can see, that curve is pretty flat. Okay, and then poorly graded, that means one size. So if I look, here's 100% passing, and all of a sudden it just drops. So basically it's pretty much one size because it's not ranging in grain sizes. And then here's my fines. Okay, so it's a really short, steep curve. Okay, so that's how we define these. Okay, so mathematically, how do we calculate those? So we call this the coefficient of uniformity, or sometimes you'll hear me say uniformity coefficient. Well graded, so what is well graded again? Well graded is uniform. It's flat curve. If I have a coefficient of uniformity greater than 10, and poorly graded, steep curve if it's less than 5. Okay, so how do I calculate that? So we have, I'm going to move this guy out of the way. So you go to your 10% line, and they call it D. D stands for diameter, you know, is the same as the grain size, right? And you project a line over until you hit your curve, and you project straight down. Okay, and then this is the grain size at 10% passing. So 10% of your grain sizes in that sample are 10% smaller than that size. Okay, and then D60, diameter at 60% passing, I find my 60% passing on my y-axis, and then I project over, and I come straight down, and then that's my grain size. Okay, and then what I do is I take D60 divided by D10, those two mathematical numbers, rounded to the nearest whole number, and then this will determine if I'm well graded or poorly graded. So I get this question all the time, what happens if it's in between? So that's a very good question, because soils aren't perfect. Okay, a lot of our soils in Wisconsin in the glaciated areas are poorly graded because they've been washed, they've been eroded, they've been transported downstream, so, and they're all one size. Okay, so let's go back to our curve and calculate the coefficient of uniformity. So if you look at this curve, it's definitely not gap graded. It doesn't do this like a slide. It's not well graded because it doesn't flat around there. So most likely this is a poorly graded. Okay, so I'm going to, let me do a focus lock here. All right, so first thing we do, all right, is, yes, you need to do everything that you do a hidden line horizontally until I hit the curve. This is why it's important that you draw your curve correctly, make it look like it's uniform. And this is why we round it to the whole number, because every curve is going to be a little bit differently. Okay, all right, so it hits the curve, and looks like it hits right there. I drop down. So then what you're going to do is you're going to write D10 equals, what size is that? So this is 0.01. So that means it looks like that curve intersects at 0.09. So I'm going to write that right there, 0.09 millimeters. All right? So when I look at it, I can do a quick check as an engineer. Yep, that looks about right. Okay, let's find our D60. Yes, it's a coincidence that one of our sieves actually had 60% passing. It's a coincidence. All right, so we come down, we intersect, and we come straight down. This is why this semi-log paper is great. Okay, make sure you don't write through your lettering. All right, D60. Okay, so what size is that? So this is 0.1. I'm going to say 0.6 equals 0.6 millimeters. Okay, now what I'm going to do, I'm going to write CU equals D60 divided by D10. That's the formula, right? And then what I'm going to do is I'm going to put D60, 0.6. So this number is this coefficient of uniformity is a dimensionless number. 0.6 divided by 0.09. Okay, I want to see this. Nice and neat. Got plenty of space in here. So if I take 0.6 divided by 0.09, I get 6.67. I want to round that to the nearest number, so that equals 7. And then I'm going to box in my final answer. Okay? So I just calculated coefficient of uniformity. All right? So the next question is, one thing I forgot to add on this is, you know what I didn't do? I did not put a title on my graph. So we need an x-axis, units, a y-axis label, units, and then we need a title. So let me see if I can get the title up here. So we're going to go this, obviously, so what you're going to do, so this is going to be, for example, green and gold quarry, 3/4 inch stockpile. It's going to be boring 1, sample 1. It's going to be something like that. Sieve size, grain size versus percent passing versus sieve. So this is, see, I have my guidelines here. Example, percent passing versus grain size. So even though I have sieve size here, grain size means the same thing. But typically it would be identified as something here. Quarry, stockpile 1, etc. Grain size. Nice and neat, all one height. Okay? So as you can see there, okay, so I have a x-axis label, y-axis label, and a title chart. So we just calculated a coefficient of uniformity. Okay, so going back to the presentation. Okay. Now the last thing we're going to talk about is the fineness modulus. Okay, FM, fineness modulus. The fineness modulus is an indication of the fineness of the aggregate. In general, the higher the fineness modulus, the coarser the aggregate. Okay, so basically we have more pass, more retain on the coarser aggregate. Okay, it's used in concrete mix design to estimate portions of fine and coarse aggregate. So this is a number. It's rounded to 2 decimal places. Okay, basically they use that number. So based on that number, there's charts and design. So if I have this, if I'm going to use this much coarse aggregate, and depending on my fineness modulus, it can determine how much weight of fine aggregate I need. So we get that nice well-graded mix, so we fill in all the little voids, okay? So it's not an exact science, but it helps us determine the portion of the coarse aggregate and the fine aggregate together, okay? So that's what that's for. So let's calculate your fineness aggregate. And if you look here, let me go talk about the sieve size. Use the following sieves. We never use the 200 sieve, and then we start at the 100 sieve, that's the smallest sieve, and then we double in size as we get bigger. So 100, number 50, if you look at the size, number 30, okay? How come there's not a 25? There is no number 25 sieve. Don't ask me why. Then, half of number 30 is number 15, but we don't have a 15 sieve, we have a 16. Half of 16 is number 8, so we do have a number 8 sieve, a number 4 sieve. See the size is doubling, and then 4.75, and then double that size, I get 9.5. So 3 inch and a half, double inch and a half, we get 3 and 6 and 2. So basically you add them all up until you run out of sieves, okay? So let's calculate that. So on our sheet. All right, so escape, let's go to here. All right, so with that, okay, so if I look at my percent passing, I'm not going to use the, so this is cumulative, okay? FM is cumulative percent passing. So I'm going to use the 100 sieve, 50, 30, 16. I'm not going to use the 10 because it's not double. I'm going to use the number 8 and the number 4. Okay? So that equation is, so obviously I don't think I wrote it down, is I'm going to add these up and divide it by 100. It turns it back into a decimal. Okay? So I'm going to just, let's see here, I'm going to use a separate piece of paper. Fineness modulus equals cumulative percent retained, okay, the sum of the cumulative percent retained of those certain civs, which I just talked about, divided by 100, okay, and then 2 decimal places, okay? All right. So with this, so maybe if I show this together, so I start with the 100. So I got 80.7 plus 60.0 plus 40.0 plus 26.0 plus, so I'm not using the number 10, right? I'm not using the number 10. Oops, sorry. Hopefully you can see that. So as you can see here, let's go again. In this case, it got blurry. Cumulative percent retained number starting with 100 and then go double the sieve size. Make it double the size. So 80.7 plus 60 plus 40 plus 26. I gotta go from 16 to a number 8, so it didn't include the number 10. So number 8 is plus 0.7%. Then plus 0.0%. I add all those together and I divide by 100. Basically, it gets it back from a percentage to a decimal. And we want 2 decimal places. So 80.7 plus 60.0 plus 40.0 plus 26.0 plus 0.7 plus 0.0 equals. So I get 206.77 divided by 100 equals 2.0677. So 2 decimal places, which equals, so basically I just move this back 2 spots, right? So that's 2.07 equals my finest modulus. So this number is how coarse that is, okay? I didn't do a lot of research on this. I don't really quite, I'm just going to be honest with you, I don't quite really understand this number, but it's used in proportioning. I don't know what the ranges of those numbers are, okay? So, again, going back, it's an indication of the finest. So the larger this number, okay, if we look at this, so obviously if we have more cumulative percent retained on the smaller sieve sizes, right? So that means the aggregate's coarser, correct? Okay. So, or I'm sorry. So these are the large, the sieve openings get larger as I go up. So if I have more cumulative up here, okay, that's going to make this number, let's see, 80 point, oh yeah, right? Yes, so if these numbers are bigger, it's going to make this number bigger. So that means I'm going to that's going to make this number bigger. That means I'm going to need more fine aggregate, because you can see the numbers small, passing to number 4. So this is all fine aggregate, okay? So this will help us determine how much coarse aggregate, the ratio between coarse and fine aggregate, okay? All right, so that explains that. So slideshow from current slide. Okay, so there is a section in your book, in the textbook, under finest modulus. If you go in the index and type finest modulus, you read about it, maybe it'll help you understand it better. So it's a ratio, that's what it is. It's a mathematical ratio they use us to do mixed design. All right, so we did that. Okay, so I'm going to stop the presentation now. We're going to review WSDOT Section 501 and ASTM 333. What I'm going to do is I'm actually going to put that lecture underneath your homework so you understand the homework, because I want to go over the homework so you understand what it is. I don't want to include that in this because this is getting long enough. Okay, so with that, we are done with this lecture. This is the end of lecture LP2, okay? This is part 2, and then look forward to LP2 part 3, which I'll put in your homework. So, thank you for your attention.